Hi guys, welcome to GM Maths' first YouTube video. This is going to serve as a supplementary resource to the tutoring that we are doing. We're going to begin by covering interesting topics generally, just to get the formatting down, and then we're going to move on to covering the A-level content in a structured way that you can hopefully learn from. So this video beginning is going to be optional stopping theorem. We're going to start with what I think is a really interesting problem, show how optional stopping theorem helps us solve it, and then how we can apply that to other similar problems. I think it was the most interesting thing I learned at uni. Let's get into it. Okay guys, let's get started. So we're doing the intro to optional stopping theorem, OST. Let me start by introducing this problem that I was talking about. We have a six-sided die that we roll repeatedly. And I say, I'm going to play against you and I win if I roll a 4, then a 5, then a 6 consecutively. Jesus. And you win if you roll a 6, and a 6 consecutively. Now, the question is, who has the advantage? Who's more likely to win? Who's more likely to see this come up first? Have a little think. I'm going to guess that you're saying that it's a fair game. It's an independent die. Each roll is independent of each other. Therefore, 666, 456 equally likely to happen. That is in fact wrong. And we're going to look at why right now. So now we move on to the stall. This part is the hardest to follow. It seems unconnected to the problem, but it's actually a great way to understand how we get to the answer, and it also introduces optional stopping theorem very nicely. So we're going to start by calculating the expected rolls to get 666 consecutively. We have a stall. Ran by me. And there is the dice being rolled. So every day we have a new better come. They come and they bet £1 that it's going to be a 6 that day. They bring £1. If they're wrong, we keep it. If they're right, we give them £6. Including the initial £1 that they gave us. So the two options are, let's look at the payoffs here. Which is the same as saying net minus £5 versus net £1. Okay, so what you can see from this is that clearly this is a fair game. There's a 1 in 6 chance that we lose £5, and there's a 5 in 6 chance that we lose £1. So overall, the expected value of this game is £0. Is 0. The net transfer money is 0, but if you're taking it this way, he pays £1, the expected value is £1, and so fair game. Now, this is where it gets interesting. Each day is fair. What will happen though, if they win, they take that £6 and they play the next day. Forget the stall. And they play the next day with their £6. You have the £6 here coming in, but you also have a new £1 coming in. And this £6 is back on 6 again. So what do we then have? You have the same payoff you'd expect, where if they win, you pay 36 to the man who bet 6, and you pay 6 to the person who bet 1. So now let's look at the end of this, when we finally get 666 in a row. We have player 1. Oh, sorry, we have player n minus 2, bets £1, gets £6, gets £36, walks away with. So we get 6, a 6, and a 6. They walk away with 216 pounds. Player n minus 2, player n minus 1. Enters here with £1. They swap over for £6 and they exit here with £36. And finally, player N enters with his £1, with their £1, sorry, and leaves with 6. So in the end, once we lose, we know that we pay out. Go to black here, sorry. We know in the end, we pay out. My maths is incredible here. 258. I think that's right. So we pay out £258 at the end. That we know that is what happens when we lose, or when we get 6, 6, 6 consecutively. And until then, any money that is won, if there is a 6, is then given straight back to us on the next roll when it's not a 6, or the roll after. So what do we know about this game? We know that the payout at the end, the payout is 0 up until the final 3 rolls, where we pay out 258. And how much money do we make? We make N pounds. Now, what do we know about this game? We know that at every stage, every stall, it's a fair game. Meaning, what we expect to pay out equals what we expect to make. The question we have, and what seems like should work, is that we can then extrapolate that because each stall is a fair game, we can then say that playing this game 5 times is a fair game. Is still fair. Seems fair enough. Playing it N times is still fair. Now this is where we get on to stopping times. This is more advanced probability, and it's essentially the idea that you aren't stopping after a fixed number of times. You're stopping based on some outside condition. And it's actually not true that because a game is fair at each step, that it will be fair no matter what strategy you adopt. Here, the strategy is you bet in this way until you get 3 6s, and then everyone stops. It's not actually guaranteed that that will be a fair game, which is where we use optional stopping theorem. But just to finish this example, optional stopping theorem does say that this is still a fair game. Betting in this strategy still doesn't give either side an edge. And therefore we can say n, expected value of n, we have expected payouts, pay equals expected make, therefore expected n equals 258. Therefore n equals 258. Cool. Now we repeat this for 4, 5, 6. This will be much quicker this time, since hopefully you understand this. It's the exact same model, except now person number 1 bets that it's a 4. If they're wrong, the next person will come and bet that it's a 4. Wrong, and then they'll bet it's a 4 again. It is a 4. Now they go, the next 2 people come and they bet that it's a 5. So instead of going 6 every time, it's 4, 4, 4. Once it's a 4, you bet it's a 5. Once it's a 5, after a 4, you bet that it's a 6. And so we get the same idea with 4, 5, and 6. Now, sorry, this person still bets that it's a 4 because everyone has to have the same strategy. Everyone has the same strategy. So this person bets that it's a 4. This person bets that it's a 5. Works that way around. Now, skip the rest of it. What do we end up getting? Let's look at the payout. So n minus 2. We have player n minus 2 here. They come in, they bet on £1 that it'll be a 4. And it is a 4. So they bet £6 that it'll be a 5. And it is a 5. And it is a 6. Okay, we already have that. £36 that it'll be a 6. But now we have player 2. They bet £1 this could be 4, and they don't win. They just leave. Same goes for player N. They just leave. And so now we analyze at the end, payout actually just equals 216. Therefore expected. So 4, 5, 6 wins as a marginal edge. A couple questions here that you might have. We're going to go more into stopping theorems, stopping times, optional stopping theorem, do it more rigorously. But the question might be, why isn't it that person comes, he bets 4 is correct, he now switches to a 5, but person B bets 4. as their first guess? Why can't we just, if they get 5 as their first guess, then suddenly we get 258 instead of 216. The problem there is, and this is martingales, this is the next topic that this also leads into, is these people have to be independent for optional stopping theorem to apply. That's the first part of it. And so if this person is using knowledge from a previous event, they're not independent of person A because they're using information person A has that's not available. Then they're using a different strategy to person A. The person A bets on 4. So person B has to adopt the same strategy, which means starting off with a 4, and if they're correct, betting 5, then 6. Hopefully that answers the question and gives a little insight into, and so I said we'd finish off by applying this to things. This idea of the iterative people and the stalls can be used for basically any dice game. If it's how long until I spell out my own name by taking random letters, you can work that out. Anything you want to do, you can use this as a much faster way to directly calculate the expected waiting time, rather than using what you probably used to use, where you go the likelihood of an event and then try and use binomial or whatever it is that based on the problem